Okay, lastly, let's take a look at the special case of the carbon dioxide molecule. There are a couple things we want to look at. Two of them are fairly trivial, but one is really, really interesting. It has to do with the symmetry of the molecule. Let's take a look. Okay, here's a sketch of our carbon dioxide molecule. And I've taken the particular case of a CO2 molecule where the carbon is carbon-12, and then the two oxygen atoms are both oxygen-16 atoms, the most common isotope. So most of them are like this, but I suppose some could be different isotopes. So what do we need to be aware of? First, in order to do our calculations, we need to know what the moment of inertia of this molecule is about its center of mass, or about the rotation axis, actually, which in our case goes right through the center of mass, goes right through the carbon atom. I'll let you work this out, but I just want to remind you that in general, for a system composed of point particles, the moment of inertia is the sum over each of the particles of the mass of the particle times the distance from the rotation axis to the particle squared. So we have to compute that. Secondly, when you want to investigate the vibrational frequencies, for that we need to know the reduced mass, okay? And to calculate the reduced mass for a particular vibration, we also need to be a little bit careful. The vibrational mode that we're interested in is the asymmetric stretching mode. In this molecule, the oscillation looks like this. The carbon atom moves in one direction, and the oxygen atoms move together in the opposite direction, okay? So really, because the oxygen atoms move together, you can think of lumping them together as one particle with twice the mass. That is, this should have the same effective mass as this, where I have one particle whose mass is twice the mass of an oxygen atom, and a second particle whose mass is just the mass of the carbon atom. And now these would oscillate. Oscillate in the normal way if they were connected by a spring and set to move. So now it's not hard to find the effective mass of this pair, which we're saying is equivalent to the mass of the effective mass of the carbon dioxide molecule for this particular mode. Now, those two considerations are pretty trivial. This third consideration is very interesting, at least very interesting to me, and it has to do with the symmetry of the molecule. The CO2 molecule that we've drawn is symmetric about the carbon atom, and in particular, the two oxygen atoms occupy equivalent positions. Moreover, they're identical quantum particles. And in fact, oxygen-16 atoms are integer spin 0. They are not spin 0, they're spin 1. So they are bosons, okay? And as you're learning, there are interesting properties for quantum systems that are made either all of bosons or all of fermions. And for bosons, the important thing is that the wave function of the entire molecule must be symmetric under exchange of these two bosons. So if we have an operation where we exchange the oxygen atoms, then the wave function has to remain completely unchanged, okay? Now, because this molecule is symmetric, we can exchange the oxygen atoms simply by flipping the molecule over, by inverting it. So the wave function for this molecule must be symmetric under inversion, okay? Now, let's look at that more closely. So the wave function for the molecule can be thought of as the product of three different terms. One term describes the electronic state, the state of all the electrons in the atom molecule, particularly the valence electrons. The next is the vibrational state, and the third is the rotational state. Okay? Now, what's interesting in that is that in the ground state of the molecule, the electronic state is already symmetric under inversion. It's a sigma orbital, in other words. Moreover, in the vibrational ground state, where nu equals 0, the vibrational wave function is also symmetric. It's like the ground state of a harmonic oscillator. And so that means that the inversion symmetry of the entire molecule is determined by the inversion symmetry of the rotational part of the wave function. And this is quite interesting. For states that have rotational quantum number which is even, the rotational wave function is symmetric. But for states where j is equal to an odd number, the rotational wave function is asymmetric. Okay? Now, because the oxygen atoms are identical bosons, that means that only this first state is allowed, because the total wave function has to be symmetric. Okay? So odd values of j are not allowed for a carbon dioxide molecule in its ground state, provided the two oxygen atoms are identical. So as a result, this means that for the ground state, j can take on only even numbers. Here, I started to write an odd number, but 0, 2, 4, 6, and so on. From the point of view of that spectrum, it means that half the lines that we might expect if we were unaware of this are going to be missing. Okay? Because the molecule can't occupy any initial state that has j equal 1, 3, 5, and so on. Those states simply don't exist for the ground state when the molecule is in its ground vibrational state. Isn't that fascinating? On the other hand, if you were to do something to the molecule that made those two oxygen atoms non-identical, or if made the entire molecule so that it's not symmetric under exchange of the, so they're not in equivalent positions, this would all go out the window. So we could imagine, like, suppose I could put a little dab of paint, on one of the oxygen atoms. So that would break the symmetry. And if anything that breaks the symmetry would mean that the odd states, that these would be allowed. For example, if one of these was an oxygen 18 atom instead of an oxygen 16 atom, okay? About 0.1% of oxygen is oxygen 18. Or if the molecule were in a vibrational state which also broke the symmetry. In cases like that, the odd parity states would be allowed, and suddenly you'd expect twice as many lines in the spectrum. Okay, I think that's interesting, so I wanted you to be, and it's important for analyzing data from carbon dioxide, so I wanted you to be aware of it.